In the last video, we talked about Dalton's postulates, and we talked about Thomson's work with cathode ray tubes, which led him to discover the electron and develop this plum pudding model of the atom. And remember, the key value that Thomson determined was the charge to mass ratio for the electron. So what that means is if now someone could either solve for the charge or the mass of the electron. They could use Thomson's ratio, which was correct. We now know that it was correct in order to figure out the other value. So now we're going to talk about the work of Millikan. And Millikan is best known for the oil drop experiment. And that's going to determine the charge on the electron, and then he can use Thomson's ratio in order to figure out the mass of the electron. So he's best known for determining the charge of the electron using the oil drop experiment. The second point here, it says it shows that the negative charge was quantized. So that just means, quantized just means that it's delivered in discrete amounts. It can't be any amount. So the electron has a specific charge and can only be delivered in those increments. So this is more or less a schematic of the oil drop experiment setup. So there's kind of a lot going on here, but I think when all is said and done, it's a relatively straightforward idea. So we can kind of work our way down. So first, Millikan has this kind of spray bottle to shoot oil droplets into this upper chamber. And he's able to shoot X-rays at the top chamber, and essentially what happens with the X-rays is they're interacting with air molecules, whatever they may be in that upper chamber, and causing electrons to eject off of the surface of the air molecules, and then these electrons end up sticking to the oil droplets. So essentially at this point, he's got oil droplets of relatively consistent size, and electrons that are floating around are adhering to these various oil droplets. So now what I have at this point is oil droplets in this upper chamber with some number of electrons stuck to them. It could be 1 electron, could be 5 electrons. Some number of electrons have stuck on to this oil droplet. Then between the two chambers, we have a tiny opening. So electrons are going to fall to the bottom of the chamber, the top chamber, and then fall through this opening into the second chamber. So in the second chamber, we've got these electrically charged plates. So there's a negative charge on the bottom and a positive charge on the top. And so essentially the field strength in that second chamber can be adjusted, and then here is where he's able to observe the oil droplets. So remember, these oil droplets that are arriving in the second chamber, they have some number of electrons adhered to them, so they have some amount of negative charge associated with them. So notice that the bottom plate is negatively charged. So if I increase the field strength sufficiently, then there's going to be a repulsion from that negatively charged plate, and I guess an attraction from the positively charged plate, that will enable the electron to be suspended in that second chamber. So kind of like with Thomson, we can think about math that we don't want to get too involved in, but here's the general idea. once Millikan knows the field strength required to suspend the oil droplet, that's going to be information that he'll be able to use to figure out uh, essentially the charge associated with that oil droplet, the amount of field strength required. So it's important in order to do that that he knows the mass of the oil droplet that he's observing, and that's where the observer space is important because he knows the density of the oil, and he can observe through his observing lens over here. He can observe the diameter of the oil droplet. So then, using the volume of the oil droplet and the known density of the oil he's using, he can figure out the mass of the oil droplet. And the reason that's important is because the force acting on that oil droplet due to gravity is a function of the mass of that oil droplet. So he needs to know that information in combination with the field strength required to suspend the oil droplet, and that'll be what he needs in order to figure out the charge on that oil droplet. So let's go back again, right? So some number of electrons are stuck onto this oil droplet. It might just be one, but it could also be multiple electrons on the oil droplet. So what Millikan ends up finding is that every time he does this experiment, he finds that all of the total charges divide evenly into the same number. So he comes up with a number of 1.6 times 10 to the negative 19 coulombs, which is the unit of charge in the SI system. I think really the main unit of charge we always talk about. And so either it's an incredible coincidence or that's the smallest unit of charge that's possible, meaning that's the charge on a single electron. So a little more complicated here, I think, than the previous experiment with all the things that are going on here, but hopefully that makes okay sense. So I guess to briefly summarize, right, oil droplet enters chamber, electrons stick onto oil droplet falls into second chamber. Knowing the mass of that droplet and the field strength required to suspend the droplet is enough information to figure out the charge on that droplet, and all of those charge numbers he calculates divide evenly into this number that I wrote in the upper right corner. So knowing the charge, he can also go back to Thomson's ratio and figure out the mass. So we now know that the numbers that Millikan got were perfectly accurate and totally acceptable numbers. So that all worked out, and the number he has is the number we still use now. All right, so that didn't change the model of the atom that Thomson proposed, right? The plum pudding model idea is not impacted by Millikan figuring out the charge and mass of the electron, but now we know more about this fundamental particle. So we're going to move on to talk about the gold foil experiment that was conducted by Rutherford. But in order to do that, we need to really briefly talk about radioactivity because Rutherford's going to use a specific alpha particle in his experiment that we want to talk about. So when we talk about radioactivity, it refers to the spontaneous emission of radiation by an atom. So spontaneous doesn't mean anything about how quickly it happens. It means it's something that happens without any outside intervention. So it occurs naturally. The first person to observe this effect of radioactivity is Henry Becquerel. And I think he was on the timeline because it comes in with our gold foil experiment. I think the people most famous for studying radioactivity are Marie and Pierre Curie. So for our purposes, we don't need to know too much about radioactivity, but we need to know a little bit about Rutherford's work in this area, specifically to talk about alpha particles. So what we've got in this picture is we've got this lead block that contains some element that is radioactive, meaning it spontaneously decays. I think he used radon in his actual experiment. But anyway, there's a substance in this container. It has an opening so that as radioactive decay occurs and these particles are released, they're going to travel in a specific direction. So Rutherford found 3 particles. Alpha particles, which are what we're interested in, that are positively charged and have a mass substantially larger than an electron. There's also beta particles, which are really just electrons themselves that are being released through radioactive decay. And then the third radioactive decay particle, I guess we can call it, that was observed are called gamma rays, and those are photons of light. So those are just particles of light. So Rutherford is going to use these alpha particles in his experiment because they are substantial in mass compared to the electron, and because they're positively charged, so they will be directed toward the electrons. So when we think about this experiment, that's the most important thing, that it's substantial enough in mass that it would be able to knock electrons out of its way, and it's positively charged, so it's likely to head toward those electrons. Okay, so Rutherford receives the Nobel Prize for the gold foil experiment. He actually worked with Thomson prior to conducting this experiment. And later on, he will also be credited with discovering the proton as he continues his study of the atom. So let's look at the schematic for Thomson's plum pudding model. And the most important thing to think about in the plum pudding model is it's essentially vacant space with electrons kind of randomly scattered through that space. So if I were to shoot alpha particles through the atom, and this was indeed what the atom looked like, all of the alpha particles would go straight through based on what this model looks like. One, because it's primarily vacant space, but 2, because if the alpha particles encountered electrons, they're large enough that we would expect them to knock them out of the way and go straight through. So that's the premise that we enter the gold foil experiment with. The expectation that the alpha particles are not going to encounter any resistance. They're just going to go straight through an atom. So let me draw this here, I guess, before we get to that. The basic idea then of the experiment to start with was to shoot alpha particles at a piece of gold foil, so as atomically thin as could be easily achieved at this time. It's not atomically thin, but only a few atoms thick, presumably. And then he had a detector, I think just a coated screen that would show alpha particles colliding with the screen. So the expectation would be that 100% of particles go through. If the plum pudding model is accurate, that's what we would expect. Let me just say expectation. And to be fair, right, you're not supposed to go into a science experiment with expected results necessarily. See what it tells you and then go from there. But that's the expectation, assuming the plum pudding model is correct. I think I told you earlier it's not correct, and we're gonna see that. So essentially, they did this experiment that I'm describing: alpha particles through through a sheet of gold foil with a detector directly behind it, expecting to see 100% of the particles go through. Well, that's not what happened. The majority of them went through and hit the detector, but there were some that they could not account for. So with that idea in mind, here's a better look at the apparatus that they used for the experiment. So here's our alpha particle source. Here's the gold foil that we're shooting it at. But notice now, rather than a screen directly behind the gold foil, now it's a wraparound screen. So essentially, having not detected all of the alpha particles, they figured, let's build a screen all the way around it to see if maybe they're going elsewhere. Okay, so then this is kind of what I was talking about before. The expectation was all alpha particles will go straight through these plum pudding atoms because it's either vacant space or electrons that the alpha particles can easily knock out of the way. But the observation is what we see over here is some. So again, the majority went through and hit the detector right behind the gold foil, but some of those particles end up undergoing some amount of deflection and they hit the screen elsewhere. Okay, so down at the bottom here, I kind of wrote a little summary of this. Rutherford shot alpha particles at a thin sheet of gold foil and observed the pattern of scatter of the particles. Based on Thomson's model, he expected all of the particles to go through the foil. And then here I said, although the majority of particles went through, some particles were deflected by the gold foil, indicating Thomson's model was incorrect. So in the picture here to the right, in the very center of these atoms, you can see that there are these little dots, and those are nuclei. So Rutherford's conclusion is essentially that there must be a concentration of mass somewhere in there big enough so that if the alpha particles bumped into it, they would get deflected back out, right? The only rational explanation for the alpha particles not all going through is that they encountered something of greater mass that deflected them back out. So this leads to the proposal of the atomic nucleus, which is a much more accurate version of the atom and a lot closer to the model we're going to stick with for the upcoming chapters. So with regard to the experiment, this is a picture of what we would expect. So here you're seeing the majority of atoms passing right through the space. Oh, I circled one that did not pass right through. But some of them here and here are encountering the actual nucleus and getting deflected back out. I guess this one and this one as well. So still the majority we would expect to go through, but if they did indeed encounter the nucleus, they'd be deflected at some angle. So this is what I was saying. The particles must have encountered a heavy mass inside the atom. So with that idea in mind, the fact that the majority of the particles went through tells us only a small volume is occupied by this nucleus, since so few of the particles were actually deflected. So it turns out that when we actually look at the atom, the understanding that we have now is pretty consistent with this. So like I said, since so few of them were deflected out, Rutherford proposed a very small, dense nucleus where the electrons are circulating around it. So still the case that most of the volume of the atom is empty space. That makes sense because most of the alpha particles went through, but a small number of them encountered the nucleus, and were bounced back out at some angle of deflection. So here it's telling us about dimensions of the nucleus relative to dimensions of the atom. It's kind of hard to understand from this picture because in order to make a visible nucleus on this page relative to the atom, it's already substantially exaggerated in size. I think your book says if we want to compare the size of the nucleus to the size of the atom itself, I think it says it's a if the atom is a stadium, the nucleus is a blueberry in the stadium. So I guess that's a more appropriate look at it rather than this dot that we can clearly see in the larger sphere. Okay, so here's a picture kind of describing what's going on in this case. So it shows the nucleus as this tiny dot in the larger atom. So you can see here the dimensions it's talking about, 10 to negative 10 meters for the for the atomic diameter, and 10 to the negative 15 for the nucleus diameter. So then what's the model at this point? The model at this point is to say that there are protons, and later they'll discover neutrons, packed tightly into this nucleus. So that's where all the mass and all the positive charge is located in the atom. And then electrons are circulating around this nucleus that has positive charge. So the electrons are attracted to it and they circulate around it. So that leads us to something called the planetary model of the atom. And that's where we kind of want to start with as we begin thinking about the atom. And we'll refine it a little bit later, but that's a good place for us to start. So this is kind of a cool little cartoon I found that shows us what's going on. I guess we are here for now, right? So we started with Dalton and just his simple, solid, spherical model. We call it the billiard ball model. Then we got to Thomson with his plum pudding model, and now here we are with Rutherford. So what you can see is the nucleus in the center, the concentration of positive charge, and then all of these electrons circulating around that positively charged nucleus in various fixed orbits. So that's more or less what Rutherford tells us, and relatively quickly we move to the planetary model with Niels Bohr. We'll talk about his work in a few chapters, but more or less this is the model of the atom that I want you to be thinking about as we go forward. So we've got this concentration of positive charge in the center, and then these electrons are circulating around that positive charge in various fixed orbits. That's why we think about it as the planetary model. When we're all done talking about the model of the atom, which will be a few chapters away, that's when we'll get to a quantum model, but we're not there yet. So somewhere between Rutherford and Bohr, that's the picture of the atom that we're going to live with for the upcoming chapters. Okay, I think one or two more slides, and then that's it for this section. So as Rutherford continues his work studying the atom, he officially discovers the protons in 1919, and then there's another particle discovered by James Chadwick a bit later called the neutron. And like it sounds, the proton has a positive charge, neutron has a negative charge, electrons have the negative charge, neutrons are neutral, that's why they're called neutrons. All right, so where does that put us in terms of these particles? Well, we've got protons and electrons, those have a charge, right? Neutrons say neutral, so that's what they should be, neutral. Protons and neutrons have essentially the same mass, and comparatively, the mass of the electron is so small that we can ignore it. So most of the time, we're going to talk about protons as being +1 and electrons as being -1. In reality, those charge units are not +1 and -1. Remember, we have the charge of the electron in terms of coulombs, so the proton would be positive 1.6 times 10 to the -19 coulombs, and the electron is negative 1.6 times 10 to the -19 coulombs. But like I said, a lot of the times we're just going to say +1 and -1 for the purpose of describing the atom. And then, of course, despite me saying exactly the opposite, neutrons are neutral. So now what we've got is mass values in atomic mass units. And the atomic mass unit you can see written down here, it's 1.66 times 10 to the -24 grams, so a really small amount. We mentioned atomic mass unit in the very beginning of this section when I was just telling you it's also called the Dalton in honor of Dalton's work for developing atomic theory. So in atomic mass units, you can see here's our value for the proton, here's our value for the neutron, very, very close together, so essentially one atomic mass unit. But then when you go to the electron, you can see it's substantially smaller. So that's consistent with Thomson's observation that whatever he was seeing had a much lower mass than anything we had ever seen before, because it's, 5,000 times or 2,000 times lower than the mass of the proton and the neutron. So what we'll see is, and we'll get to this fairly quickly, what we'll see is for the purpose of determining the mass of an atom, the electron mass is so low that we can ignore it. So that's what this bullet point means here, that for the purpose of calculating the mass of an atom, the mass of an electron is so small that we can ignore it. Okay, I think the last one's just blank like usual. So that's the end of chapter 2, part 1. More or less, that's the picture of the atom that we're going to work with for the next few chapters. So somewhere between this nuclear model and planetary model, we'll talk about how those are actually different once we get to that section. But a general picture of positively charged nucleus and negatively charged electrons circulating around it, that's the picture that we want to have for the atom going forward. Okay, so I'll go ahead and stop here. We'll pick up in the next video with the chapter 2, part 2 slides.